This is the EdExcel A-Level Further Maths Paper 3 from the 2022 series, and in this video we will be taking a look at the Decision 1 module. Question number 1. A gardener needs the following lengths of string. All lengths are in meters. So here we have the lengths of the strings in meters. She cuts the lengths from balls of string. Each ball contains 10 meters of string. For part A, we have to calculate a lower bound for the number of balls of string the gardener needs. You must make your method clear. So, for part A of the question, we begin by adding together these lengths, and then we will divide this by 10. The reason for that, we know each ball contains 10 meters of string. And so if we work out this calculation, well, we have 4.3 plus 6.1 plus 5.1 plus 4.7 plus 2.5 plus 5.9 plus 3.4 plus 1.7 plus 2.1 plus 0.4 plus 1.3. So we get 37.5, and then we divide this by 10. And if we work that out, it turns out we get a value of 3.75. So what we can conclude then is the lower bound is 4 balls of string. For part B of the question, we have to use the first fit bin packing algorithm to determine how the lengths could be cut from the balls of string. So for part B, here we have our length of the strings, and the first thing we can do is open up a new bin. We'll call this bin bin 1. Now, when empty, the space in bin 1 is 10. Now we place the 4.3 into bin 1, and if we do that, we can cross off the 4.3, indicating we've used it already. And so the space left over then in bin 1 will be 10 subtract 4.3, which is 5.7. Let's take a look at the 6.1. Well, currently there is not enough space to put the 6.1 into bin 1, and so we open up a new bin and place this 6.1 into it. So when we open up a new bin, we have space 10, and now that we've placed the 6.1 into it, the space left over will be 10 subtract 6.1, which is 3.9. Let's cross off the 6.1, indicating we've used it. Let's take a look at the 5.1. Well, what we can see is there is enough space in bin 1 to place the 5.1 into it, so we can place the 5.1 into bin 1, and the space left over then will be 5.7 subtract 5.1, which is 0.6. Let's cross off the 5.1, indicating we've used it up. Let's take a look at this 4.7. Well, there is not enough space in bin 1, there is not enough space in bin 2, so what we need to do is open up a new bin. Bin 3, say. So when we open up a new bin, the space is 10. We place the 4.7 into it, and so the remaining space will be 10 subtract 4.7, which is 5.3. So let's cross off the 4.7, indicating we've used it up. Now, if we take a look at the 2.5, there is not enough space in bin 1, however, there is enough space in bin 2. So, we place the 2.5 into bin 2, and the remaining space then will be 3.9 subtract 2.5, which is equal to 1.4. So now let's cross off the 2.5, indicating we've used it. Let's take a look at the 5.9. Well, there is not enough space in bin 1, there is not enough space in bin 2, there is not enough space in bin 3, so what we need to do is open up a new bin. Bin 4, say. So when we open up a new bin, it's got space 10. We place the 5.9 into it, and when we do that, the space left over, 10 subtract 5.9, is equal to 4.1. So now let's cross off the 5.9, indicating we've used it. Let's take a look at the 3.4. There is not enough space in bin 1, there is not enough space in bin 2, however, there is enough space in bin 3. So we place the 3.4 into bin 3, and so the remaining space will be 5.3 subtract 3.4, which is equal to 1.9. So now let's cross off the 3.4, indicating we've used it up. Let's now take a look at the 1.7. There is not enough space in bin 1, there is not enough space in bin 2, however, there is enough space in bin 3. So we can place the 1.7 into bin 3, and so the space left over will be 1.9 subtract 1.7, which is equal to 0.2. So we cross off the 1.7, indicating we've used it. Let's take a look at the 2.1. Well, there is not enough space in bin 1, there is not enough space in bin 2, there is not enough space in bin 3, however, there is enough space in bin 4. So we place the 2.1 into bin 4, and so the remaining space will be 4.1 subtract 2.1, which is 2.0. So let's cross off the 2.1, indicating we've used it. Let's now take a look at the 0.4. Well, there is enough space in bin 1 to place the 0.4 into it. So we place the 0.4 into bin 1, and therefore the remaining space will be 0.6 subtract 0.4, which is 0.2. Let's now cross off the 0.4, indicating we've used it. If we take a look at the 1.3, there's not enough space in bin 1, however there is enough space in bin 2, so we place the 1.3 into bin 2, and so the remaining space will be 1.4 subtract 1.3, which is 0.1. Let's now cross off the 1.3, indicating we've used it. We have sorted the original list into appropriate bins. Question number 2. Figure 1 represents a network of cycle tracks between 10 landmarks A, B, C, D, E, F, G, H, J and K. The number on each edge represents the length in kilometers of the corresponding track. One day, Blanche wishes to cycle from A to K. She wishes to minimize the distance she travels. For part A, for the first part, we have to use Dijkstra's algorithm to find the shortest path from A to K, and we have to, for the next part, state the length of the shortest path from A to K. So here we've got this diagram which we can use to help us find the shortest path from A to K, and we've got this key, we've got the vertex, the order of labeling, the final value and the working value. So we start at A and we finish at K. So if we start at K, 0 will go in the working value, and so in the final value we will put 0, and the order of labeling will be 1. Then we have 0 plus 8, which is 8. 0 plus 18, which is 18. 0 plus 14, which is 14. The smallest from 8, 18 and 14, that will be the 8. And so the final value will be 8, and the order of labeling will be 2. So now, taking a look at what comes off B, 8 plus 9 is 17. 8 plus 23 is 31. 8 plus 4 is 12. The smallest from the 31, the 12, the 17 and the 14 is the 12. So the final value will be 12, and the order of labeling will be 3. So now let's take a look at what comes off E. Well, we have 12 plus 16, which is 28. We have 12 plus 3, which is 15. We have 12 plus 17, which is 29. And we have 12 plus 31, which is 43. So now the smallest from 14, 43, 29 and 28 and 15, that is the 14. So 14 will be our final value, and the order of labeling will be 4. Let's take a look at what comes off D. Well, 14 plus 14, that's 28. 14 plus 25, that is 39. So the smallest from the 28, 39, 15 and 28, that will be the 15. So 15 goes into the final value, and the order of labeling will be 5. So now let's take a look at what comes off C. Well, here we would have 15 plus 10, which is equal to 25. So now the smallest from 25, 39 and 28, that will be the 25. So 25 is our final value, and the order of labeling will be 6. So now if we take a look at what comes off the F, we have 25 plus 10, which is 35. So now the smallest from 35 and the 28 is the 28. So 28 will be our final value, and the order of labeling will be 7. So now let's see what comes off H. We have 28 plus 6, which is 34. We have 28 plus 23, which is 51. And we have 28 plus 33, which is 61. So now the smallest from the 34, the 61 and the 51, that will be the 34. So 34 is our final value. The order of labeling will be 8. Let's see what comes off G. Well, 34 plus 25, that is 59. 34 plus 10 is 44. So now the smallest between the 44 and the 59 is 44. So 44 is our final value, and the order of labeling will be 9. And then we have the 59 left over, so the 59 is our final value. The order of labeling will be 10. So here is our completed network using Dijkstra's algorithm. And now what we have to do is find the shortest path from A to K and the length of the shortest path from A to K. Well, the length of the shortest path from A to K, that quite simply is 59. And the shortest path, well, to work that out, well, we start at A, and then we go to B, and then we go to E, then we go to H, and then we go to G, and then we go to K. So therefore, the shortest path from A to K, we have A, B, E, H, G, K. The cycle tracks between the landmarks now need to be inspected. Blanche must travel along each track at least once. She wishes to minimize the length of her inspection route. Blanche will start her inspection route at D and finish at E. For part B, for the first part, we have to state the edges that will need to be traversed twice and then find the length of Blanche's route. Well, here is the activity network. Let's find the order of each node. For A, we've got 3. For B, we've got 4. For C, we've got 4. For D, we have 3. For E, we have 5. For F, we have 4. For G, we've got 6. For H, we've got 5. For J, we have 2. And for K, we also have 2. So what we can see then is the odd nodes are A, D, E, and H. So we have A, D, E, and H for our odd nodes. And we know from the question at D, and we finish at E. And so we need to go from A to H. So to go from A to H, well, we can go A to B. That has 8 as its weight. And then we can go B to E. That has 3 as its weight. And then we can go from E to H. That has 16 as its weight. And so, therefore, the edges that need to be traversed twice are the shortest routes from A to H, and these are AB, BE, and EH. So now when we come to find the length, what we have is the 299 and what we add this to is the 8, the 3, and the 16. So we add 299 to 8 to 3 to 16, and if we work this out, we end up with 327 kilometers. It is now decided to start the inspection route at A and finish at K. Blanche must minimize the length of her route and travel along each track at least once. So, for part C, by considering the pairings of all relevant nodes, we have to find the length of Blanche's new route. You must make your method and working clear. So, for part C, we've got our activity network as we see here. And we know that A, D, E and H are odd. Now, there's a couple of things we need to consider. First of all, we start at A and finish at K. We were told that in the question. And what you will find is A is odd, but K is even. And so, we need to make K odd and D, E and H even. This ensures that we start at A and finish at K. A is already odd, K is even, we need to make that odd, and because D, E and H are already odd, we need to make those even. And the way we can do this is by repeating edges. Now, as we've just said, A is already odd, so we do not need to include that in the pairings. So if I consider the pairings of D, E, H and K, well, if we consider first of all D, E, I need to start at D, I need to finish at E. So from D to E, we can go from D to A, then to B, then to E. So to go from D to E, we need to go via A, B, and then we end up at E. So we've done D and E, now we need to go to H to K. So for us to go from H to K, well, H to K, we could go directly. Alternatively, we could go via G instead, because that will be shorter. 6 plus 25 is smaller than the 33. So we could go from H to K via G. That's one possible pairing. Now we could go D to H. Now for us to go from D to H, so we want to start at D, finish at H. The way we could do that is we could go to D, then to F, then we could go to G, and then we could go to H. That's the smallest way. So DH, we can go via FG. And then we've got H. And then we've got the pairing EK. So for us to go from E to K, we could go E to H, H to G, and then G to K. So the way we can go from E to K is via H, G. And then we've got the K. Now we've got DK. So from D to K, we could go via F and then G and then going to K. So we have DK via F, G, and then we add on to this E, H. So E to H, well, that's just 16. So now we can find each of these. So if we work each of these out, well, D to E via AB, we've got 14 plus 8 plus 4, that's 26. And then H to G to K, so we've got H to G to K, so that's going to be 31. So it turns out what we get over here is 57. Then we've got D, F, G, H, so we've got D, F, then G, then H, so we've got 14 plus 10 plus 6, so that's 30. And then E to H, so that's 16 plus 6 plus the 25, that's 47. So if I add these together, it turns out we get 77. And then D to F, that's 14. F to G, that's 10. And then to K, that's 25. So altogether we have 49. And then we add on to this EH, which is 16. And if we work all of this out, it turns out we get 65. So what is the smallest we have? Well, the smallest we have is the 57. So what can we conclude from this? Well, the length of the new root is 299. So that is the original. And then we add on to this the 57. And it turns out we will get 356 kilometers. Question number 3. The initial distance matrix in Table 1 shows the lengths in meters of the corridors connecting 6 classrooms, A, B, C, D, E, and F in a school. For safety reasons, some of the corridors are one way only. So here we've got Table 1. And for part A, by adding the arcs from vertex A along with their weights, we have to complete the drawing of this network on diagram 1 in the answer book. So here is diagram 1, and here is table 1. Now A to B is 12 and B to A is 12, that's fine. So we can connect those straight away like so with 12. Then we've got A to C, which is 32, and C to A, that's 32. So here we have 32. Then we've got A to D. A to D is 24 and D to A, that's 24, so that's also fine. We can add an arc like that with 24. And then we've got A to E, which is 29, and E to A, which is infinite. So from A to E, that's one way. So we put an arrow like this, and then we've got the 29. And then we've got A to F, which is 11, and FA, which is also 11. So we can connect those like this. The 11 goes here. So here is the completed diagram. Floyd's algorithm is to be used to find the complete network of shortest distances between the 6 classrooms. The distance matrix after 2 iterations of Floyd's algorithm is shown in Table 2. We have to perform the next 2 iterations of Floyd's algorithm that follow from Table 2, which should show the distance matrix after each iteration. So after 2 iterations, B has been considered, so we have to consider the C's remaining the same, and on the 4th iteration we've got the D's staying the same. Now for convenience, here we've got the 2nd iteration where the B's remain the same. So now if we fill in the column and the row for C for the 3rd iteration, we've got 29, 17, 4, 12, and 40. And going across, we've got 29, 17, 4, 12, and 40. So now if we consider what goes in this element, we compare the sum of 17 plus 29 with the 12. We can see the 12 is smaller, so that remains as it is. For this element, we compare the sum of 29 and 4 with the 20. We see the 20 is smaller, so 20 remains here. For this element, we compare the sum of 29 and 12 with the 29. 29 is smaller, 29 goes here. And then for this element, we compare the sum of 29 and 40 with the 11. 11 is smaller, so 11 remains as it is. Next, for this element, we compare the sum of 29 and 17 with the 12. The 12 is smaller, so 12 goes here. Next, for this element, we compare 17 and 4 with the 8. 8 is smaller. For this element, we compare the 17 and the 12 with the 41. 41 is bigger than 17 plus 12. 17 plus 20 is 29. So 29 goes here instead. Then we compare 17 plus 40 with the 23. We see 23 is smaller, so 23 remains the same. Now, if we take a look at what goes here, we've got 29 plus 4 being compared with the 24. 24 is smaller, so 24 goes here. And now for this, we compare 17 plus 4 with the 36. 17 plus 4 is smaller, that's 21. So we change to 21. And then we compare 4 plus 12 with the 53. We see 4 plus 12 is smaller, so we put the 16 here. Then we compare the 4 plus 40 with the 13. The 13 is smaller, so that stays as it is. Next, we compare 29 plus 12 with infinity. We see 29 plus 12 is smaller, that's 41, so 41 goes here. We now compare 12 plus 17 with the infinity. 12 plus 17 is smaller, so that 29 changes. Then we compare the 12 plus 4, which is 16, with the 18 over here. So the 16 goes here. And then we compare the 12 plus 40 with the 12 over here. So the 12 remains as it is. We now compare 29 plus 40 with the 11. 11 is smaller, so that stays as it is. We then compare 17 plus 40 with the 23. 23 is smaller. We then compare the 40 plus 4 with the 13. The 13 is smaller. And then we compare 40 plus 12 with the 12. 12 is smaller. So here we have completed our third iteration. Let's now complete the fourth iteration. Well, the D column stays the same, so we've got 20. We've got the 8, then we've got the 4, then we've got 16, then we've got the 13, then we've got 24, 21, 4, 16, and 13. So now we need to repeat this process. So we compare the 21 plus 20 with the 12 over here. 12 is smaller, so 12 goes here. We then compare this 29 with 4 plus 20. 4 plus 20 is smaller than 29, so 24 goes here. We then compare 16 plus 20 with the 29 here. 29 is smaller, so 21 stays the same. And then we compare 20 plus 13 with the 11 over here. 11 is smaller, so 11 stays as it is. We now compare 24 plus 8 with the 12 over here. The 12 is smaller, so it stays the same. We then compare 4 plus 8 with the 17. 4 plus 8, which is 12, is smaller, so that changes. We then compare 8 plus 16, which is 24, with the 29 here. 24 is smaller, so that changes. And then we compare 8 plus 13 with the 23. 8 plus 13, which is 21, is smaller, so 21 goes here. Next, we compare 24 plus 4 with the 29 here. 24 plus 4, which is 28, is smaller, so that changes. Next, we compare 21 plus 4 with the 17 here. 17 is smaller, so 17 goes here. We then compare 4 plus 16 with the 12. 12 is smaller, so 12 goes here. Then we compare 4 plus 13 with the 40 over here. 40 is bigger, so 4 plus 13, that's 17, that goes here. Next, we compare the 24 plus 16 with the 41. 24 plus 16, which is 40, is smaller, so that goes here. Next, we compare the 21 plus 16 with the 29. 29 is smaller, so that stays. We then compare 4 plus 16 with the 12. 12 is smaller, so that remains the same. We then compare 16 plus 13 with the 12. 12 is smaller, so that remains the same. We then compare 24 plus 13 with the 11. 11 is smaller, so that remains the same. Then we've got 21 plus 13 being compared with the 23. The 23 is smaller. And then we compare 4 plus 13 with the 40. 4 plus 13 is smaller, so the result of that changes. So we've got 17 here. And then we've got the 13 plus 16 being compared with the 12. 12 is smaller, so that remains the same. Here we have completed the fourth iteration. The final distance matrix after completion of Floyd's algorithm is shown in Table 3. Yinka must visit each classroom. He will start and finish at A and wishes to minimize the total distance travelled. For part C, for the first part, we have to use the nearest neighbour algorithm starting at A to find two Hamiltonian cycles in the completed network of shortest distances, and then find the length of each of the two cycles. Well, here is a copy of Table 3, and what you will notice is A to C, that's 24, whereas C to A, that's 28. So this is a question where we have to apply the algorithm by reading across the rows instead of the columns. So we start off at E. So we place a 1 next to the E, and then we delete the entire column of E, as we see here. Now, reading across, the smallest one we can choose is 12. Now, we can either choose the 12 here or the 12 here. I'm going to choose the 12 here. And what that does is it takes me to C. So I place a number 2 here. So what I've done so far is gone from E to C with 12 as my distance. And now if I delete column C, like so, reading across from C, the smallest one is this 4. And that takes us to D. So, we put a number 3 where D is, and then we delete the entire column of D as we see here. So, reading across from D, we see the smallest one is the 13. And that takes us up to F. So now we are at F, so we place a number 4 where F is, and then we will delete the entire column of F as we see here. So now if I read across F, the smallest one is the 11, and that takes me up to A. So now I'm at A, so I can put a number 5 where A is, and then I can delete the entire column of A as we see here. And if I read across, the smallest one will be the 12, which takes me up to B. So I've got 12, which takes me across to B. So now we can delete the column containing B as we see here, and then we've got a 6 here. So now that we are at B, we need to go back to E, and if we go back to E, well, B to E, that's 24. So here is one Hamiltonian cycle. We've got 12, 4, 13, 11, 12, and then the 24. And if I add these together to find the appropriate length, it turns out we get 76 meters. Now let's repeat that again. We start off with 1 where E is, so we are starting off where E is. Then the next thing we do is we delete the entire column where E is. We look across E and we look for the smallest one. Now before we chose the 12 here, which corresponded to C, what we could have done instead is choose this 12 over here, which corresponds to F. And then our next step is to delete the column containing F, and we put a number 2 where F is. So now we read across F, and the smallest one is this 11. So now that we are at F, we go to A next. So we put a number 3 where A is, and then we delete the column containing A. So now we read across A, and the smallest one now is this 12 here, which takes us to B. So now we are at B. We delete the column containing B. So we put a number 4 here. And now that we are at B, we read across for the smallest one, which is 8. And that takes us to D. So now we can delete the column containing D, and we put a number 5 where D is, and then we read across. The smallest one is this 4. So we go from D to C. That's 4. And that takes us to C. And now that we are at C, we delete the column containing C. And then we look across C because we want to get back to E. And that's 12. So now what we need to do is add these together. And if you work this out, it turns out we get 59 meters. So we add the 12, the 11, the 12, the 8, and the 4, and the 12, we get 59. Now, if we go back to the question, we were asked for the third part to state with a reason which of the two cycles provides a better upper bound for the length of Yinka's root. So what we see then is this cycle, EFABDCE, is the better upper bound because it contains a smaller value. The 59 is smaller than the 76. Question number 4. A linear programming problem in X, Y, and Z is to be solved using the Big M method. The initial tableau is shown below. For part A, using the information in the above tableau, we have to formulate a linear programming problem. You should list each of the constraints as an inequality and state the two possible objectives. So, the way we can go about this is to first of all write each of these as equations. So for part A, if we take a look at the S1 row, we've got 2x plus 3y plus 4z, and then we've got S1 this is equal to 13. And if we write this as an inequality, we would have 2x plus 3y plus 4z is less than or equal to 13. If I now take a look at the A1 row, I've got 1x, I subtract 2y, I add 2z, then I subtract a surplus S2, but then I add an artificial A1. The result of this is 8. Now because I'm subtracting a surplus and adding an artificial, this would imply I've got a greater than or equal to. So when I come to write my inequality, we've got x subtract 2y plus 2z is greater or equal than 8. If we take a look at the A2 row, we've got 3x, 0y's, and then we subtract 4z. We subtract a surplus S3, but then we add an artificial A2. The result of this is 12. Now, because I'm subtracting a surplus and adding an artificial, this would mean when I write this as an inequality, we would have 3x subtract 4z is greater or equal than 12. And now, if we consider the non-negativity, we would have x, y, and z all being greater or equal than 0. Now, if we take a look at the objective function, well, what we have so far is p. Then what I'm doing is I'm going to subtract 2 minus 4m x, and then I'm going to subtract negative 3 plus 2m y, and then I'm going to subtract negative 1 plus 2m z, and then I'm going to subtract m s2, and then I'm going to subtract an m s3, the result of which is negative 20 m. So what we can do from this is expand and simplify. So we would have p. Now here I've got negative 2x, then I've got positive 3y, and then I've got positive z, and then I have if I factorize out an m, I have positive 4x subtract 2y subtract 2z subtract s2 subtract s3 m, and this is equal to negative 20 m. So we have p subtract 2x plus 3y plus z subtract, well, if I set this equal to, I would have negative 4x plus 2y plus 2z plus s2 plus s3 subtract 20 m. So what does this mean? Well, if I concentrate on what I have on the left hand side, we can maximize minus 2x plus 3y plus z, which is the same as minimizing 2x minus 3y minus z. So here are two possible objective functions. For part B, we have to obtain the most efficient pivot for a first iteration of the big M method. You must give reasons for your answer. First of all, we know that M is big. And because M is big, the only negative in the objective row is 2 subtract 4M. That will be this over here. This will give us a negative entry because we are subtracting 4 lots of a very, very big number from 2. So what that means is the pivot is in the X column. So now if I applied the ratio test, well, in the S1 row, I've got 13 divided by 2, which is 6.5. In the A1 row, I've got 8 divided by 1, which is 8. And in the A2 row, I've got 12 divided by 3, which is 4. So what that means is the 3 in the A2 row is the pivot. So this 3 in the A2 row is the pivot. Question number 5. The network in figure 2 shows the activities that need to be completed for a project. Each activity is represented by an arc and the duration of the activity in days is shown in brackets. The early event times are shown in figure 2. For part A, we have to complete table 1 in the answer book to show the immediately preceding activities for each activity. So here we've got table 1, and I've provided a copy of the network. Now what you can see is A, B and C rely on nothing. So for each of those we can put a dash. Now if we take a look at D, D depends on A only. So we can put an A over here, and E relies on C only. Now, if we take a look at F, that relies on C only. If we take a look at G, well, what's feeding into G is certainly E and B. But because we've got a dummy over here, that means A is also feeding in to G over here. So that means G relies on A, B, and E. And if we take a look at H, which is over here, well, it's the same argument. We've got A, B, and E feeding in to H. So we have A, B, and E. Next, if we take a look at J, which is over here, well, we've got D and G feeding in to J. And if I take a look at K, well, what's feeding into it is F and H. What we've also got, because of this dummy, is D, and we also have we've got the dummy there and the dummy here, which would imply that K relies on D, G, H, and F. So what we have done here is completed our network. we are now given that 4 is less than x, which is less than or equal to m. We have to state the largest possible integer value of m. Well, here is our table. Now, if we think about the difference between 7 and 16, that difference is 9. So 16 subtract 7 equals 9. And what we also see is 14 subtract 4, that's 10. Now, what does this mean? Well, if I had a 10 over here, or the weight of f, that means I will not get 16 for the early event time. So I'm restricted by this branch here, which means the largest possible value of m is 9, not the 10. Which means when I write down my inequality, we've got 4, which is less than x, which is less than or equal than 9. Next, we have to complete diagram 1 in the answer book to show the late event times and then state the activities that must be critical. So, we have the 22, which would go here. Now, if I work backwards, well, 22 take away 6 is 16. There's nothing to compare it with. And if we assume that the dummy has a weight of 0, so we've got 0 here and 0 here, well, 22 take away 7, that's equal to 15, and 16 take away 0, that's 16. The smaller one is the 15, so 15 goes here. Next, if we do 15 subtract 3, that's 12. And if I do 16 subtract 5, that's 11. So 11 would go here. If we continue to work backwards, we have 15 subtract x, and then we compare that with 11 subtract 0. Now the smaller one will be the 15 subtract x, and let's think about why that's the case. What we know so far from the previous part is x is certainly bigger than 4. So if I have 15 subtract something bigger than 4, I get something smaller than 11, which is why 15 subtract x is smaller than the 11 with this condition. And if we work out 11 subtract 4, that's 7. And if I do 16 subtract x, well, certainly what is smaller is 7. Because if I do 16 subtract 9, which is the biggest possible value, I get 7, and anything bigger than 4 but up to and including 9, 16 subtract x is bigger than the 7. So the 7 would go here. And now, working backwards even more, 15 subtract x, subtract another 4 from that, that's 11 minus x. Then I've got 11 subtract 5, which is 6. And then I've got 7 subtract 7, which is 0. Of course 0 is the smallest one. So now at this point, what we need to do is find the critical activities. Well, 0 plus 7 is 7. Then we have 7 plus the 4, which is 11. Then we have 11 plus 5, which is equal to 16. 16 plus 6 is 22. And so therefore, the critical activities will be C, E, H, and K. These activities are critical. For part D of the question, we have to calculate the total float for G. So to calculate the float of G, well, G is over here, so we would have the 15, subtract the 3, subtract the 11. So to calculate that float, we would have 15, subtract the 3, subtract the 11. And if I work this out, the float of G is just 1. The resource histogram in figure 3 shows the number of workers required when each activity starts at its earliest possible time. The histogram also shows which activities happen at each time. We have to complete table 2 in the answer book to show the number of workers required for each activity of the project. So here we've got table 2. Now here's a copy of the resource histogram. Let's take a look at A. A requires 3 workers. So A requires 3 workers. If we now take a look at B, that's got a height of 2 over here, and here we also have a height of 2. What's really happened is this bit over here has fallen down to here. But either way, B has 2 workers which it requires. If we take a look at C, well, you can see C requires 1 worker. If we take a look at D, what you can see here is D requires 2 workers. If we take a look at E, that requires 2 workers. Now if I take a look at F, F requires 1 worker. G, that requires 2 workers. H, that requires 2 workers. J requires just 1 worker. And K, you can see that requires 3 workers. So here is the completed table. For part F, we have to draw a Gantt chart on grid 1 in the answer book to represent the activity network. Now, if we go back to our activity network, before we do anything else, we need to actually find the value of x so we can show the float times. So here we've got grid 1, and this is where the Gantt chart will go. Now, if we take a look at the histogram, one thing you will find is D has a weight of X. So let's take a look at D before anything else. D starts at 4. Okay, that's where D starts. And D finishes over here at 10. Which means that the duration of D is 6. So, from the resource histogram, we saw that D starts at 4 and finishes at 10, which means it's got a duration of 6, which means X is equal to 6. Now, going back to what we found earlier, we found the critical activities to be C, E, H, and 6, and that takes us up to 22. So, if we show those, like so, we've got C with a duration of 7. So that takes us up to here. Then after that, we've got E, so that takes us up to 11. Then after that, we've got H, which takes us up to 16. And then after that, we've got K, which takes us up to 22. Now, A and B do not rely on anything. So we've got A with a duration of 4. So this is where A will go. And then B has a duration of 5. So this is where B goes. What we now need to do is show the appropriate floats. So if I calculate the float for A, knowing that X is equal to 6, 15 subtract 6 is equal to 9. So the float of A is equal to 5. So showing the float of A, that takes us up to 9, as we see here. So this is the float of A. If we take a look at B, the float of B, well, from 6 to 11, the float is going to be 6. So that takes us up to 11. So 11 is over here. So there is the float of B. Now, if I take a look at D, the earliest D can start is 4, and it's got a duration of 6, and therefore its float then will be 5. So D starts, it's got a duration of 6, so that takes us up to 10. So this is where D is, and then we've got a float of 5, so that takes us up to 15, which is over here. So we've done D. Now the next one is critical, so after that is F. So F starts at 7, and it's got a weight of 6. So if I show F, F starts at 7, which is over here. It's got a weight of 6, so 1, 2, 3, 4, 5, 6. So that finishes at 13. And therefore the float will be just 3. 7 plus 6 plus another 3 is 16. So the float then will be 3, as we see here. So this is F. Then we've got G. So G starts at 11 and it's got a duration of 3. So here is where G is, duration of 3, and the float of this, well, 11 plus 3 plus 1 is 15. So it's got a float of just 1. So we've done G. H and K are critical, what's left over is J. So J starts at 14, duration of 7. So with a duration of 7, that takes us up to 21. And then we've got the extra bit from 21 to 22, that's 1. So the float is going to be 1. So here is the resource histogram, and we've got the critical activities, which are these activities here. So as I've just redone, we've got the appropriate Gantt chart as we see here. Question number 6. The following algorithm determines the number of comparisons when Prim's algorithm is applied to Kn. For part A, for K5, we have to complete the table in the answer book to show the results obtained at each step of the algorithm. Now, we are considering K5, which means n is equal to 5. Now here, we've got the table. We will place the output here, which is step 10 of the algorithm. So the output would correspond to step 10. And I've created an extra column where we will put the relevant steps. So the first thing we will do is start the algorithm. So step 1 would be for us to start the algorithm. So the second step is to input the value of n. The value of n is equal to 5. The third step is to let a equal 1. The fourth step is to let b equal n minus 2. So for the fourth step, we will let b equal 5 minus 2, which is 3. For the fifth step, we will let c equal b, so c is equal to 3. For the sixth step, we let a equal a plus 1. So we take our current value of a, we add 1 to it, we get 2. Our seventh step is to let b equal b minus 1. So we take our value of b, we subtract 1 from it, we get 2. Our eighth step is to let c equal our current value of c plus a times by b plus a minus 1. So let's work this out. We've got our current value of c, which is 3. We add on to this a times by b, so we have 2 times by 2, and then we add on to this a minus 1, so we have 2 minus 1, and it turns out we get 8. Our ninth step is to question whether if b is greater or 0, and if it is, we go to step 6. So is this value greater than 0? Yes it is, so we will go to step 6 And if we go to step 6, at step 6, we let a equal a plus 1. So a plus 1, 2 plus 1, that's 3. Our 7th step is to let b equal b minus 1. 2 minus 1 is 1. Our 8th step is to let c equal c plus a times by b plus a minus 1. So we've got c, which is 8, plus a times by b, so we have 3 times by 1, plus a minus 1, so we have 3 minus 1. It turns out we get 13. Our 9th step is to question whether b is greater than 0. And if it is, we go to step 6. So we can see the 1 is greater than 0. So we go back to step 6. And at step 6, we let a equal a plus 1. So 3 plus 1 is 4. Step 7, we let b equal b minus 1. 1 minus 1 is 0. And then step 8, we let c equal c plus a times by b plus a minus 1. So we take our value of c, which is 13. We add on to it a times by b, so we've got 4 times by 0. And then we add on to this a minus 1. So we have 4 minus 1. And it turns out we get 16. And now we question if b is greater than 0. Well, b is equal to 0 here. So in this case, we go to step 10, which is our output. We then output c. The output of c is 16. And then we stop the algorithm. So here is the completed algorithm with an output of 16. For part B, the weights of the 10 arcs in figure 4 are shown here. We've got 17, 21, 24, 14, 23, 13, 15, 19, 28 and 20. Starting at the left hand end of the list above, we have to sort the list into ascending order using bubble sort. You need only write down the state of the list at the end of each pass. And then we have to find the total number of comparisons performed during the sort. So I've created this table. We've got the pass, which we will record, and then the number of comparisons for each pass, and then we've got the original list of numbers. So we begin with the first pass. We compare 17 and 21. 17 is smaller. So now we compare the 21 with the 24. 21 is smaller. So now we compare 24 with the 14. 14 is smaller. So 14 goes here. And now we compare the 24 with the 23. 23 is smaller. So that 24 we compare with 13. 13 is smaller. We compare the 24 with the 15. 15 is smaller. We compare the 24 with the 19. 19 is smaller. We compare the 24 with the 28. The 24 is smaller. So now we compare the 28 with the 20. We see that 20 is smaller. So what goes at the end of the pass is 28. So for the number of comparisons then, we made 9 comparisons. Next, if we take a look at the second pass, well, the 28 will remain where it is. We compare 17 with the 21, 17 smaller. We now compare 21 with 14, 14 is smaller. So now we compare this 21 with the 23, 21 is smaller. So now we compare the 23 with the 13, 13 is smaller, and we now compare the 23 with the 15, 15 is smaller. Compare the 23 with the 19, 19 is smaller. 23 with the 24, 23 is smaller. So now we compare the 24 with the 20, 20 is smaller. So now what's moved to the end of this pass is the 24. So that's not changing for the third pass, and neither is the 28. So when we come to write down the total number of comparisons, we made 8 comparisons there. Next, for the third pass, we compare the 17 and the 14. 14 is smaller. Compare 17 and 21. 17 is smaller, so now we compare the 21 with the 13. 13 is smaller. We compare 21 with 15. 15 is smaller. 21 with 19. 19 is smaller. 21 with 23. 21 is smaller. We now compare the 23 with the 20. 20 is smaller. And what's moved to the end of this pass is the 23. So those aren't going to change in the next pass. When we come to write down the number of comparisons we made 7 of them. For the fourth pass, we compare 14 with 17, 14 smaller. We compare 17 and 13, 13 is smaller. We compare 17 and 15, 15 is smaller. 17 and 19, 17 smaller. 19 and 21, the 19 is smaller. 21 and 20, the 20 smaller. So the 21 moves to the end over here. We made 6 comparisons, and for the fifth pass, 21, the 23, the 24 and the 28 are not going to change. Next, we compare 14 and 13, 13 is smaller. We now compare 14 and 15, 14 is smaller. We compare 15 and 17, 15 smaller. So compare 17 and 19, 17 is smaller. Compare the 19 and the 20, 20 is larger than the 19, so the 20 would move here. What we made here is 5 comparisons. And then for the sixth pass, the 20, the 21, the 23, and the 24 and the 28 stay the same. Now we compare the 13 and the 14, no swaps. 14, 15, no swaps. 15, 17, no swaps. 17, 19, no swaps. So each of those numbers stay as they are. And what we made here then is 4 comparisons. So now, when we come to find out the total number of comparisons we made, we add together the 9, 8, 7, 6, 5 and the 4. What we see is we have 39. Comparisons. For part C, we have to find the maximum total number of comparisons required to sort the weights of the 10 arcs of K5 into ascending order using bubble sort. Well, the maximum number of comparisons, that will be 10 multiplied by 10 minus 1 divided by 2. So the maximum number of comparisons then is 45. It is given that the maximum total number of comparisons required to sort the weights of the arcs of Kn into ascending order using bubble sort is lambda n times n minus 1 times n plus 1 times n minus 2, where lambda is a constant. We have to determine the maximum total number of comparisons required to sort the weights of the arcs of K50 into ascending order using bubble sort. You must make your method and working clear. For part D, we know that when n is 5, in other words for K5, the maximum number of comparisons is 45. And if I substitute this into my formula, I've got lambda multiplied by 5 multiplied by 5 minus 1 multiplied by 5 plus 1 multiplied by 5 minus 2. So we've got 45 equals 360 lambda, which means lambda is equal to 1/8. And so therefore, when n equals 50, we can find out the maximum number of comparisons in this case. We have 1/8 multiplied by 50 multiplied by 50 minus 1 multiplied by 50 plus 1 multiplied by 50 subtract 2. So if we work this out, we've got 1/8 times 50 times 49 times 51 times 48. It turns out we get 749,700. So therefore, we've got 749,700 comparisons. Question number 7. Figure 5 shows the constraints of a linear programming problem in X and Y, where R is the feasible region. The objective is to maximize P equals X plus KY, where K is a positive constant. The optimal vertex of R is to be found using the Simplex algorithm. For part A, we have to set up an initial tableau for solving this linear programming problem using the Simplex algorithm. So, for each of these equations, let's find the corresponding inequality. So if I take a look at y equals 2x plus 1, I want the region underneath this line, which means I want y to be less than or equal to 2x plus 1. If I take a look at the 7x plus 2y equaling 46, well, if we rearrange this so we have y equals, we would have y equals minus 7 over 2x plus 23. And what I want is the region underneath the line, which means my inequality is y is less than or equal to minus 7 over 2x plus 23. If we now take a look at the line x plus y equals 8, well, here we have y equals negative x plus 8, and if we take a look, we want the region underneath the line, which means that y is less than or equal to negative x plus 8. And if we take a look at this line here, we can rearrange so we've got y equals minus 1/2 x plus 6, and what we want is the region underneath the line, which means when I rearrange and write down my inequality, I've got y is less than or equal to minus 1/2 x plus 6. So now what we will do to set up our initial tableau is we'll write each of these inequalities as equations using surplus variables. So here we've got each of our inequalities. Now, everything involving x's and y's will move to one side, and everything that doesn't involve an x and a y will move to the other side. So if I take a look at this first inequality, if I rearrange, I've got minus 2x plus y less than or equal to 1. If I take a look at the next inequality, if I also multiply by 2, we would have 7x plus 2y, which is less than or equal to 46. If we take a look at the third one, we've got x plus y less than or equal to 8. And if I take a look at the fourth one, multiplying by 2 as well, we would have x plus 2y less than or equal than 12. So, if we were to write each of these as equations, well, here we've got minus 2x plus y plus s1 equals 1. Here we've got 7x plus 2y plus s2 equals 46. For the next one, we've got x plus y plus s3 equals 8. And for this one, we've got x plus 2y plus s4 equals 12. Now, if we also take a look at the objective function, we've got p equals x plus ky. So if we have p equals x plus ky, we can rearrange this to say p subtract x subtract ky equals 0. So now let's put each of these into here. Well, for the missing columns here, we have our surpluses S1, S2, S3, and S4. And then for our basic variables, we start off with S1, S2, S3 and S4, and then we've got P as well. So first equation, we've got minus 2x, and then we've got 1y and 1 S1. That's all equal to 1. The rest we fill in with zeros. If we take a look at our next equation, we've got 7, 2, 1. And that's equal to 46. And then these are filled in with zeros. If we take a look at the next one, we've got 1, 1 and then 1 S3. Then we've got 1 here, and then we've got 1 S3, 0, 0, 0, and then 8. And then S4, this one here, we've got 1, 2, and 1 S4. And that's equal to 12. We've got 0, 0, and 0 here. And if I take a look at what P is, I've got P minus 1 minus K, and then I've got zeros elsewhere. So there is the completed initial tableau. After 2 iterations of the simplex algorithm, a possible tableau T is shown here. What we have to do is state the value of each variable after the second iteration. Well, what we see for x here is equal to 2. So we have x equals 2. If we take a look at y is equal to 5. If we take a look at what P is equal to, that's 5k plus 2. And if we take a look at what S1 is equal to, that's equal to 1. S2, well, that's going to equal 0. S3, that's going to equal 22. And S4, that's going to equal 0. It is given that T does not give an optimal solution to the linear programming problem. After a third iteration of the simplex algorithm, the resulting tableau does give an optimal solution to the problem. We have to perform the third iteration of the simplex algorithm and hence determine the range of possible values for P. You should state the row operations you use and make your method and working clear. So for part C, we've got our table here, and I've added 2 extra columns, the row column and the theta column. Now let's call this first row R1, the second R2, the third R3, the fourth R4, and the fifth R5. Now, the first thing we need to do is identify which is the most negative entry. And the most negative entry will be this minus 2/5 plus 1k over 5. And so the S4 column is our pivot column. So now let's perform the row operations. Well, before we do that, we need to work out the theta values. We need to perform the ratio test. So 1 divided by 1/5 is 5. 2 divided by minus 2/5 is minus 5. 22 divided by 12 over 5 is 55 over 6. 5 divided by 1/5 is 25. And now the smallest positive value is this 5. So the pivot will lie in the S1 row, and so our pivot is 1/5. So now that we've identified our pivot is in the S4 column, which means the basic variable increases from S1 to S4. So our basic variable increases from S1 to S4. The rest stay as they are, so here we would have X, S3 and Y, and if here we have 1/5, what we want it to say is 1 instead of a fifth, and for the rest of them we want zeros instead. Now, because this is our pivot row, we will label this as R6. And to work out R6, this is equal to, well, to go from the 1/5 to the 1, we need to divide by 1/5, which is the same as multiplying by 5. So we have 5R1. Now, instead of a minus 2/5, what we want is a 0 instead. So the way we go about this, well, if I call this R7, to work out R7, we take R2 and then we add on to this we add on 2/5 of R6. For R8, what we have so far is 12/5 for R3. So we take R3 and then we will add on negative 12/5. In other words, we subtract 12/5 multiplied by R6. For row 9, we are at 1/5, so we take R4 and then we subtract 1/5 R6. And then for the final one, R10, well, we start off with R5, and what we want to get to is 0. So what we need to do is subtract R6 lots of this. So we subtract minus 2/5 plus 1/5 k, and then we multiply this by R6. So now we have enough information to complete the row operations. So first of all, let's multiply each of the top row by 5. So if I do that, we end up with 0, 0, 5, minus 3, 0, and then 5. Now, for the next one, we take R2 and then we add on 2/5 times R6. So if we do that, we've got 1 plus 2/5 of 0, which is 1. Then we've got 0 plus 2/5 of 0, which is 0. Then we've got 0 plus 2/5 of 5, which is 2. Then we've got 1/5 plus 2/5 of minus 3, which is minus 1. Then we've got 0 plus 2/5 of 0. And then we've got 2 plus 2/5 of 5, which is 4. Next, we have 0 subtract 12/5 of 0, which is 0. Then we have 0 subtract 12/5 of 0, which is 0. 0 subtract 12/5 of 5, which is minus 12. Minus 11/5 subtract 12/5 of minus 3, which is 5. Then we've got 1 subtract 12/5 of 0, which is 0, which is 1. Then we've got 22 subtract 12/5 of 5, which is 10. Next, we would have 0 subtract 12/5 of 0, which is 0. Then we would have 1 subtract, 1/5 we subtract. Next, we would have 1 subtract 1/5 of 0, which is 1. Next, we would have 0 subtract 1/5 of 5, which is minus 1. Next, we would have 2/5 subtract 1/5 of minus 3. So this is 1. Next, we have 0 subtract 1/5 of 0, which is 0. And then we've got 5 subtract 1/5 of 5, which is 4. The final row is slightly more complicated, especially when we deal with the case. So, here we've got 0 subtract this quantity of 0, so that's going to be 0. Similarly, we've got 0 subtract 0 times by this here, which is 0. Then we've got 0 subtract 5 times by this. So if I have 5 times by minus 2/5 plus k over 5, and then I add on to that, well, if I work out this, what we will end up with is positive 2 subtract k. And it is really important you take the time to actually write out the calculations where necessary. Next, I've got 1/5 plus 2/5 k subtract negative 2 over 5 plus 1 over 5 k times by minus 3. So if we work this out, well, I've got minus and a minus give a plus, so that's going to be plus 3 times. So if I gather together the numbers, I've got 1/5 subtract 6 over 5 which is minus 1, and then I've got 2 over 5 plus 3 over 5, which is just going to be 1. So I've got 2/5 plus 6 over 5. So that's going to be 1. So here I end up with k minus 1. And then I've got 0 plus 0, which is 0. And then here I've got 5k plus 2 subtract 5 multiplied by minus 2/5 plus k over 5. So that will be 4k plus 4. So now you can see we have completed the row operations. So now that this is complete, what we can say then is the optimal value of p is 4k plus 4, and that's what we can see here. And where would this occur? Well, it would occur when x is equal to 4 and y equals 4. So this optimal value occurs when x is equal to 4 and y equals 4. And because it's an optimal solution, we can therefore conclude that k is in between 1 and 2, but not equal to 2. And that's if we consider this situation here. We do not want any negative values, which is why it must satisfy this. Now the reason it's not less than or equal, one of the entries in the pivot row of t must be negative, which is why we have this less than. So because p is equal to 4k plus 4, if I substitute 1 in, I have 8, and if I substitute in 2, I get 12. And writing out our full solution, we have 8 which is less than or equal to p, which is less than 12.